I've talked about eigenvectors as being a really important idea related to square matrices. The eigenvectors of a matrix have lots of applications in physics. I've shown a little bit in a previous video of how they work, of how multiplying a matrix times an eigenvector gives back a constant times the same vector. There's special vectors for each matrix that do this. And so what I want to do now is talk about how do you find those eigenvalues and eigenvectors in the first place. And I'll use this matrix as my first example, 4, -1, 3, 0, as my first example of a matrix to use for this. And here's the idea. This is the defining property of an eigenvector and an eigenvalue. And I can do some algebra. I can say lambda times v is the same as the number lambda times the identity matrix times v. And then I can do some algebra and write this equation like so. I factored out m minus lambda I is the identity matrix, times v equals 0. Thus far, just ordinary math, nothing fancy. If these were numbers, I'd say, well, couldn't I just divide by this term in parentheses and find v equals 0? Eigenvectors aren't supposed to be 0. That's the whole idea, non-zero vectors. Couldn't that tell me v equals 0? Well, if they were ordinary numbers, the only way that that wouldn't happen is if this thing itself were 0. With matrices, we're a little more general. I'm not allowed, if it were the 0 matrix, obviously, that I couldn't divide by it. I couldn't find an inverse. But in general, any singular matrix doesn't have an inverse. And so if this thing were singular, that's the only way to avoid being able to multiply by an inverse and get v equals 0. So that's my criterion for finding eigenvectors. I need that the determinant of m minus lambda I has to equal 0. I need that 0, or else I'll be able to just prove that v equals 0. So this is my defining criterion for having an eigenvector, is that m minus lambda I has to be a singular matrix, that has to have 0 determinant. Let's see what that looks like for our case. In this case, this is my m, so m minus lambda I is going to be 4 minus 1, 3, 0, minus lambda I is lambda 0, 0, lambda. That's my 2 by 2 identity matrix. And so I can just go through this. This is equal to 4 minus lambda, minus 1, 3, and minus lambda. That's my matrix that I have, that's my m minus lambda matrix. And I need to say that the determinant of this is equal to 0. Now I know the determinant is 4 minus lambda, minus 1, 3, and minus lambda. That determinant is, for a 2 by 2 matrix, it's these two multiplied together minus those two multiplied together. So it's going to be 4 minus lambda times minus lambda minus 1 times 3. By the way, this fish was left for me by my 6-year-old daughter who had fun with it. I'm leaving it here just for a little bit because I think it's cute, so we're going to work around it, leaving the fish in place. So okay, what's this give me? I can multiply this out. That's a lambda squared minus 4 lambda and then plus 3. And that has to equal 0. That's my equation, the characteristic polynomial for this matrix. There we go, I've got that. And a thing to mention, by the way, in a 2 by 2 matrix, when you're finding eigenvalues this way, the equation you get is always going to be lambda squared first, minus the trace of the matrix. 4 plus 0 is the trace, adding up the diagonal. So lambda squared minus trace of matrix times lambda, plus that 3 is the determinant of the matrix. 4 minus negative 3 is 4 times 0 minus negative 3. That gives me positive 3. So that's a shortcut we're going to be able to use to do this if you don't want to multiply everything out. It's lambda squared minus trace times lambda plus determinant equals 0. For 3 by 3 and higher, you can't do that. You've got to multiply it out. But the trick works here. Okay, so we've got this. What's this tell me? This is an equation, a quadratic equation for lambda. This tells me what the possible values of lambda are that can work. So let's do that. Let's solve for lambda. In this, I can say, bring this up here, so lambda squared minus 4 lambda plus 3, I can actually see how to factor that off the top of my head. That is lambda minus 1 times lambda minus 3. lambda squared minus 3 minus 4 plus 3. That's this thing. And so my eigenvalues are lambda equals 1 or 3. So I've already gotten the eigenvalues of this matrix just by finding this polynomial and solving for lambda. That's a good first step. Next, I'm supposed to be finding the eigenvectors. And here's where we go back to the matrix and we have to sort of mess with it. We're going to use this equation right here, and we're going to solve for the v that works. So in general, what I'm going to do m minus lambda I times an arbitrary vector, I'll call it AB or something, just to give it some labels, equals 0. Let me write that down. So for lambda equals 1, I'm going to write my matrix is 4 minus 1, 3, minus 1 times AB equals 0, or 0, 0 if you want to think of it that way. And hey, if I simplify this out, my 4 minus 1 is just 3. And right now, see how this is a redundant system of equations? I get the equation 3a minus b equals 0 twice out of this. In general, you'll always have a redundant system of equations because that's the point. It's a singular matrix now. And we're finding this AB that makes this 0. So 3a minus b equals 0. That tells me that b equals 3a. And any a will work. If I choose a, I can find b. So my eigenvector, my lambda equals 1 eigenvector, in general, I can say it's a, 3a. I'm almost always going to just choose a specific representative, a specific one to be the one I look at. So I'm going to just choose 1, 3 as a good example of this eigenvector. I could have chosen minus 1, minus 3, or 2, 6, or I could have normalized it. I guess this divide by the square root of 10, 1 over square root of 10, 3 over square root of 10, whatever. Or 1 over square root of 10, 3 over square root of 10. So that's a normalized eigenvector. Normalizing is sometimes nice. That's a 10, really. I'm going to do 1, 3. That seems like a nice way of choosing one. It's nice and simple to write, so I'll do that. I'll do the same thing for lambda equals 3. Let me do that. For lambda equals 3, my matrix is 4 minus 3 is 1, minus 1, 3, and minus lambda is minus 3 times AB equals 0, 0. Equals the 0 vector. That's supposed to be 0, really. Equals 0, 0. And hey, this is another equation. It's redundant, a redundant set of equations because this had to be singular, so of course it's going to be redundant. And that tells me that, what is it? A minus B equals 0, so B equals A. So my lambda equals 3 eigenvector will be, in general, AA. Or I can choose specifically 1, 1 and be pretty happy with the eigenvector I have. That's a nice simple way of writing it. If you look back at what we did last time in the video where I was doing examples of eigenvectors, these were the 2 eigenvectors I used for the 2 eigenvalues of this matrix. And that gives you an idea of how this plays out, how this looks. You just go through this process, you find the lambda squared and all that, and you solve. And that gives you your eigenvalues, and then for each eigenvalue you go into this equation, this version, and you just solve for the vector v that does it. Important thing to notice, by the way, we've said that eigenvectors can be stretched or shrunk, and it doesn't change whether or not they're an eigenvector. That's built into this formalism. A, 3a, AA. It's built in. You'll always have that one free choice to make, at least one free choice, about the coefficients in your vector to make it work. So I hope that gives an idea of how this works, and that gives you a clear idea of how to find the eigenvectors of a matrix.